Hello teammates, it's Mr. Nanini coming to you again from the physics bunker. You're going to be watching this on the 3rd of April. I got some easy money and then I got a couple tasks for you to do. You're going to do your Poco Fiesta today and I got a small little reflection for you as well. So let's sharpen up the prudent pencil of physics. And let's get to work. So we're gonna look at pages 161 and 162. I'm gonna skip the graphs on page 160 because that needs some dialogue between you and I to make that work. We're gonna make this work though. So let's look at 3. I'm gonna ask you to think for a minute. I'm going to ask you to sketch what you think that might be. So you've got, we're building on the Earth and the Moon acting together. And we want to show qualitative vectors represent the forces that are present. So let's take a look at that. So we got the Earth, Moon. It's the only thing in the system. So that's all we have to worry about. And we know that the Earth is going to exert a force of gravity on the Moon. I'm sorry, the Moon's exerting a force of gravity on the Earth there. And the Earth exerting a force of gravity on the Moon. And we know by Newton's third law that those are equal and opposite forces. Only 2 objects in our system. If the Earth exerts a force on the Moon has to exert a force back on the Earth. Those forces have got to be equal and opposite. Even though there's a much greater mass with the Earth and the Moon, the forces are equal and opposite. And you can explain that. You can put into words, but you know that's Newton's third law, equal and opposite forces. Let's look at number 2. This takes us through some things we had done before, earlier in the year. We got a 2 kg, it's not to scale. We got a 2 kg bowling ball resting on the surface of the Earth. Yeah, you like it, my detail. Calculate the force of gravity acting. Take a shot, teammates. What's the force of gravity acting on the bowling ball? I'll give you 30 seconds. You can pause, because I'm going to dive in. So force of gravity, we know force gravity is m times g. Now we've been using that for a good bit of our time together, but this is going to help us explore. So force gravity is m times g. We're given the mass of the bowling ball, 2 kg. We know the acceleration due to gravity at the surface of the Earth is 10 meters second. So we know that the force of gravity is 20 newtons, right? Because kilogram times meters second is what a newton is. It's a unit of force, and we know force is mass times acceleration. So mass times acceleration gives us force. There we are. I told you, easy money. What's the weight of the bowling ball? So the weight is the force an object feels in a gravitational field. And so the Earth has got a gravitational field. In fact, if we were to draw field lines, the center of the Earth, if we were to draw the gravitational field that the Earth's generating, we could draw a myriad of vectors. These are just representative, right? Force of gravity, all towards the center. And so It's the force an object feels in a gravitational field, and we know the super second hour and the fighting fifth hour know that the weight of the bowling ball is exactly the force of gravity on the bowling ball. They're synonymous. It's good. So let's look at let's look at C. Assume that the Earth and the bowling ball are the only objects present. How much does the Earth weigh in the presence of the bowling ball? Now that's very interesting. So let's look at this a minute. So let's come back. Let's zoom this. Let's imagine the moon's the bowling ball. We're going to move it to the surface of the Earth. And if the bowling ball has got a weight of 20 newtons and it's sitting on the Earth and forces are equal and opposite, so the force on the bowling ball by the Earth has got to equal the force on the Earth by the bowling ball. If they're in contact, teammates prepared to be amazed. In the presence of the bowling ball, the Earth only has a weight of 20 newtons. You say, how can that be? How can that be? Equal and opposite forces. The bowling ball exerts 20 newtons of force on the Earth. The Earth can only exert 20 newtons of force on the bowling ball. That's kind of weird, isn't it? But if we were to take that to its conclusion, that's how it's got to be. And we actually answered D as we did that. Newton's third law. Every action is an equal and opposite reaction. Bowling ball exerts 20 newtons of force on the Earth. The Earth exerts 20 newtons of force on the bowling ball. That's pretty amazing. Let's continue. Let's go on to page 161. Of course, all my physics students are very happy. Holds a 1 kg physics book at the surface of the Earth. Draw a diagram of all forces in the Earth student textbook system. So we need all the forces on the Earth student textbook system. So we're going to use the book as our object. So in that Earth student textbook system, that means the only things we have to consider we got a force gravity on the textbook. 1 kg, we know that's 10 newtons. And we know that we need to have 10 newtons up. It's at rest. Those will be balanced. We're going to call it an applied force. So the Earth student textbook system, that means the only things we have to consider is the Earth student textbook. All right. Let's look at B. What is the force of the textbook on the Earth, teammates? Pause the video, think about it, and rejoin me. And you know, if it's another Newton's third law of force pair, isn't it? If the Earth imparts a force of 10 newtons on the textbook, the textbook's got to impart a force of 10 newtons on the Earth. Equal and opposite forces. Can be no other way. And think of it, if you lift, no, I'll say that example, but it's that, always come back to that Newton's third law. Recall your definition of a force is an interaction between two objects. It's a push or a pull. You've got to have two objects. Those forces acting have got to be equal and opposite. It's good. Now here's your first task for today. I want you to look at these two situations in 6. So you got a student at the top of the Earth on a scale, and the scale is going to measure the force. So it's going to measure the normal force, the force perpendicular to a surface. That scale is going to measure the force. All your objects are at rest: the Earth, the student, the ball. I want you to identify and write a short paragraph explaining under which circumstance would Atlas need to have the greatest strength. And I want you to identify, let's make it easy. Let's make it multiple choice. Let's call this case A. Let's call this case B. And is there a third case? Maybe they're equal. I don't know. If they're equal, we're going to call that case C. I want you to identify your claim and provide your evidence and reasoning to support that claim. So you're going to say, I think it is A or B or C. That's your claim and your evidence and reasoning to support that. I want a short paragraph, teammates. A sentence, that's not a paragraph. 2 sentences, nah, that's not a paragraph. 3 sentences, closer. I don't think that's a paragraph either. Enough to support your evidence and reasoning. Yes, yes? All right. And the last thing you got is your Poco Fiesta. So that's on Schoology already. That's waiting for you. It's a thinking problem. I think you're going to like it. I think we've had a very good week. I'm very proud of you. Keep going, my teammates. I wish you a great weekend, and I shall see you again on Monday. Nanini out.